A quick introduction to Julia sets for Math 355 D, Section A, Winter 2020. We've spent the semester studying dynamical systems using the family of functions f sub c of x equals x squared plus c, where x and c are real numbers. We'll end the semester with an introduction to the kinds of behavior x squared plus c can exhibit when x and c are allowed to be complex numbers. In linear algebra, we learned that a vector in R2 is an ordered pair AB of real numbers, but written as a 2-by-1 column vector AB. We call A and B the first and second components of the vector, respectively. In the same way, a complex number is an ordered pair AB of real numbers, but now written A plus BI. The I is just part of the symbol. Here, A and B are called the real and imaginary parts of the complex number, respectively. In linear algebra, we define the sum of two vectors and scalar multiplication of a real number r with a vector. To add two vectors together, a, b plus c, d, you first add the first components, a plus c, together, and that becomes the first component of the sum. And then you add b and d together, and that becomes the second component of the sum. For scalar multiplication, r times the vector ab is the vector whose first and second components are r times a and r times b, respectively. The sum of two complex numbers is defined analogously to vector addition. To add together the complex numbers a plus bi and c plus di, you first add together the real parts, a plus c, and that becomes the real part of the new complex number. And you add together the imaginary parts, b plus d, and that becomes the imaginary part of the sum of the two complex numbers. And if r is a real number, we define scalar multiplication as we did with vectors. The scalar r times the complex number a plus bi is defined to be the complex number whose real part is r times a and whose imaginary part is r times b. In linear algebra, the magnitude of a vector ab is defined as the square root of the sum of a squared and b squared. Other names for this number are norm and length. The magnitude of a complex number a plus bi is also defined as the square root of a squared plus b squared. We refer to this number as the modulus of a plus bi and denote it as the symbol you see here. In linear algebra, we don't usually define vector multiplication, except for the cross product in R3 that you probably heard about in vector calculus, and the cross product in R7, which you probably didn't hear about in vector calculus. But we do define multiplication of two complex numbers. The product of the complex number a plus bi with the complex number c plus di is defined to be the complex number whose real part is ac minus bd and whose imaginary part is ad plus bc. That all sounds rather complicated, so here are two examples that you should work out at your leisure. In writing a complex number a plus bi, it's customary to just write a if the imaginary part is 0, and just write bi should the real part be 0. Then 0 plus 0i is simply written as the number 0, and 0 plus 1i is just I. With this notation, the previous example says that I squared is minus 1, and this means in complex numbers, negative real numbers can have square roots. Since complex numbers are ordered pairs, to show them requires an entire plane. We can associate any real number r with the complex number r plus 0i. The ordered pairs r0 lie on the usual x-axis, and so we rename the x-axis as the real axis. The y-axis contains ordered pairs of the form 0s. These correspond to complex numbers of the form 0 plus si and are called purely imaginary numbers. On this picture, we've labeled the imaginary axis and the real axis, and there's the number 1 on the real axis and the number I on the imaginary axis, and a sort of random point 2 plus 1.5i. The point at which the two axes meet is called the origin. 0 plus 0i, or simply 0. The modulus of the complex number a plus bi is then the distance from a plus bi to that origin. The distance from that random complex number 2 plus 1.5i turned out to be a pretty nice rational number at exactly 2.5. Before discussing x squared plus c, we need to discuss graphs of complex functions. In calculus, plotting a function f from R to R involves ordered pairs x, f of x, and ordered pairs require 2 dimensions to plot. But if f is a function that takes complex numbers a plus bi as inputs and produces complex numbers p plus qi as outputs, then we need 4 dimensions to make a graph. 2 dimensions for the inputs a plus bi, and 2 more for the outputs p plus qi. Our vision allows us to see in 3 dimensions. We cannot see graphs requiring 4. What we can do is plot both the complex number a plus bi and the corresponding output f of a plus bi, which we will label as the complex number p plus qi, simultaneously on one copy of the plane, with an arrow pointing from the input a plus bi to its output p plus qi. As we move a plus bi around, its image, f of a plus bi, or the number p plus qi, will move around too, and we can get some feeling for the way the function f is behaving. Without revealing the actual formulas involved in the function f, this animation provides an example. First, we'll look at f of a plus bi, where the real part a is fixed and the imaginary part b changes. The images of these vertical lines appear to be parabolas. Well, except for the imaginary axis, which appears to just trace out another line, a horizontal line. Now let's consider what f of a plus bi looks like when a plus bi stays on a horizontal line. The images appear to be parabolas again, but opening in the opposite direction this time. Here's what f produces when a plus bi stays on a circle centered at the origin. These circles are a little bit flattened because I don't think I have the aspect ratio set quite right. Note that the images of circles seem to be circles or at least some kind of loops, but traced out twice for each revolution of the input circle. My ability to draw circles without the program's help is bad, but I want to illustrate how in this example the images of circles that don't contain the origin are traced out only once per revolution of the input circle. This concludes part 1 of this 2-part video. Now please enjoy part 2.